We're still talking about fully developed laminar flow, and let's just jump right into it. The last time we were talking about fully developed laminar flow, we looked at it by using Newton's second law. And just to review the equations that we worked out at that time, for a horizontal pipe, we worked out the equation for pressure drop per length across the pipe, and eventually we found out the Poiseuille's law for a fully developed laminar flow in a horizontal pipe. And I also showed you the equations and how these equations would look like if the pipe was not horizontal. If it was inclined somehow, then we would just have to account for the gravity term somehow in terms of the specific weight here. And we would also have to account for the elevation changes that are taking place from section 1, let's say, to section 2 here, and that we do by using or adding this term in here. So just keep in mind this pressure drop term here. We'll come back to this later. Moving on now to looking at this fully developed laminar flow from a dimensional analysis perspective. And you might think that we've already found out the flow rate equations or the average velocity equation, so why do we need to look at the same flow again through some other method? Well, that's because as engineers, we would like to work with something called scalable models, and to be able to scale models, to make them bigger or smaller, we need to have dimensionless terms, and these terms are not constant. They just don't have dimensions attached to them. So from a dimensional analysis point of view, for a fully developed laminar flow here, and for a constant diameter pipe, we can assume that the pressure drop across this pipe, across section 1 and 2, can be a function of, basically it could be a function of the average fluid velocity in the pipe. I'm just going to indicate that by V here. It could be the length of the pipe represented by L. It could be the diameter of the pipe, or it could be the viscosity of the fluid that is flowing within the pipe. Okay, so we have 5 terms here, and now you might think that, hang on, why not include the density term here, or maybe why not include the specific weight term as well here as a dependent variable for this pressure drop term here? Well, we don't include density in here because remember when we were looking at F equals ma, the acceleration term here was 0. So that means the right side of this equation isn't really important for our fluid analysis, and that means mass is not important. And mass for fluid flow is represented by density, so that means density is not an important variable for our pipe flow. Specific weight is not important because the flow is horizontal, so no gravity effects are being looked at right now. Gravity effects are negligible, and gamma is equal to density times gravity, so that means that we can neglect this term here too. So we have total number of variables here equal to 5, right? And this is called K, your total number of variables. And the reference dimensions, the number of dimensions that are required to analyze these equations is going to be 3. Those 3 can be force, length, and time, or mass, length, and time. So we have 5 total number of variables, 3 reference dimensions, and 5 minus 3, we get 2. And this 2 represents that we have 2 pi terms that we need to be able to work this problem out. And one of those representations is shown here. And now just by looking at this equation and looking at this pipe flow here, I can assume that the pressure drop here is proportional to the pipe length. And what that means is that as the pipe length is going to increase, the pressure drop is going to increase as well. Okay, so that's reasonable. That sounds reasonable. And we don't know what the value for this phi term here is. So I can assume that it's just some kind of constant. Let's call it C. So I can write this equation like this. And now I can move all of these terms onto the other side so I can have the pressure drop term here, or maybe I can make it into a pressure drop per length, and that would be of this type. And I can also write this equation in terms of the average velocity across the pipe too, which would be this. And if I was to use now the flow rate relationship from the continuity equation, which is Q equals area into velocity, because density across this pipe is constant. We're talking about an incompressible flow. So I can write flow rate in terms of area and velocity. And area for this pipe, because I'm looking at flow rate from this direction, right? I'm looking at flow rate from this direction. Flow rate is being represented by Q. So I'm looking at flow rate from this direction, and that means that flow rate is interacting with the cross-section on this side. And that would be the area of a circle, which is pi r squared. And the velocity value, I already know that the average velocity across this pipe. So all I have to do is I just have to plug these two in. Instead of pi r squared, I'm substituting the diameter, so it becomes pi d squared by 4. I multiply these two terms, and I get this equation. And now, if you actually look at this equation, you will see that the equation that we already saw, the Poiseuille's law, is kind of actually extremely similar to this equation. That's because it is. Because if you compare these two terms here, and if I just rearrange this equation, it becomes this, and this is exactly the same as this, except for the value for constant here. And if I equate this equation here to this one, I can find out the value for constant, right? So all I have to do is just equate this term to this one, and I will get the value for constant, which is 32 in our case. But remember that we're looking at a round pipe here. Now this value of C can change. It can change depending on the geometry of the pipe. So for the round pipe here, the value of C is 32, but say for you're talking about a rectangular pipe, that would be different now. It would be between 50 to 100 usually. So that is one of the benefits of using this dimensional analysis. We can figure out the flow rate for our fluid in terms of the geometry of the pipe as well. But the point of dimensional analysis is to find out useful dimensionless terms. We haven't done that yet. So we go back to this equation here, and we plug in the value for constant, which was C equals 32. I just plug it in here, and I bring that equation over here. And now what I can do is I can write it like this, move this term to the other side. And now I can divide both sides of this equation by something called a dynamic pressure, which is represented like this. This is the dynamic pressure term, which is density times velocity squared by 2. And actually, if you step back a little bit, you will see that this term here is actually something that you already know if you've discussed the Bernoulli's equation. And let me just put that up here. This term here is this second term in Bernoulli's equation. Okay, so it's called dynamic pressure, and you just go and review Bernoulli's equation and see how you got to this point. But all we've done here is that we've divided this entire term with the dynamic pressure on both sides. And now all I have to do is I just have to simplify this further. And when I do that, this is what my equation becomes. Or if you look at this term here, right, it's actually the inverse of Reynolds number, because Reynolds number is rho v d by mu, so it's the opposite of it, so I can write it in terms of this. And let me just now take all of this equation onto the next page to make it easier for viewing. And now I have basically found out the pressure drop in terms of, I've simplified it further. I've simplified it in terms of Reynolds number, in terms of length by d scalable factor. And what I can do is now that I can write this term as something called F, which represents the friction factor basically. And it's called the Darcy Friction Factor 2 for a fully developed laminar flow. And the Darcy Friction Factor basically predicts the energy loss within the pipe based on the velocity of the fluid, based on the resistance due to the friction, due to the viscosity of the fluid. And make sure you spot this here, that this friction term is not constant, okay? If the Reynolds number changes here, the friction term is going to change as well, because it depends on whether the flow is laminar or not, whether the flow is laminar, whether the flow is turbulent. It depends on the diameter of the pipe here. It depends on the velocity, the viscosity of the fluid. And because we're looking at laminar flow right now, so basically your friction factor is equal to 64 divided by Reynolds number. Okay, so just remember that for a fully developed laminar flow, your Darcy friction factor is equal to 64 divided by Reynolds number. And now let's just take it all to the next page again. And it's also possible that we can manipulate this equation now and try to find a different expression for friction factor. And how can we do that? We can basically take all of these terms to the other side. So we have friction factor in terms of the pressure drop now. And in the previous video, for which you will find the link here, we already found this this value out for the pressure drop. So all we have to do is we just have to plug this equation in here, right? And we have to just simplify it. So this gets canceled out the diameter, and we are left with this equation, which is basically simplified our friction factor term here, our Darcy friction factor term here, in terms of a dimensionless wall shear stress. Okay, so this is what the friction factor is about. The friction factor just predicts the energy loss within the pipe. Okay, and the energy loss within our pipe here occurs because of the viscosity of the fluid. Because the fluid is viscous, so we have layers of fluids interacting with each other here. And these layers of fluid, because they have a varying velocity here, they're causing a shear stress, which is being represented by tau W here. And because of these viscous forces, we have friction losses. We have friction that develops, that because of that, energy losses in the pipe start taking place. Okay, so now that we have looked at basically fully developed laminar flow in terms of different equations, I'm just going to list those equations here again, and just show you what we have already found out. Okay, so for the horizontal pipe, we already found out these equations. These are the important equations. And for the non-horizontal pipe, these are the equations that we found out. And right now in this lecture, we have found out the pressure drop in terms of friction factor, in terms of Darcy friction factor, and we have found out this Darcy friction factor for a fully developed laminar flow. in terms of Reynolds number and in terms of dimensionless shear stress. So now that we've looked at the physics behind the fully developed laminar flow, another aspect that we need to consider is that the energy is conserved for a pipe flow. Okay. Is energy conserved for a pipe flow? Of course it is. Of course energy is conserved. It's based on the conservation of energy principle, which is also the first law of thermodynamics, and that is applicable to every process. And because energy is conserved, we can apply the energy equation onto the pipe flow. And what that means is that we have a pressure difference to account for. We also have to account for the kinetic energy changes that may take place within our flow. Or we also have to account for the elevation changes that are taking place if the pipe is not horizontal anymore. And because of fluid friction, because of viscosity that we just talked about here, we will also have an additional term here, which is the head loss term or the pressure loss term here. Okay, so we have these four terms, and all of them should be equal to 0 in order for the conservation of energy to hold. And if I want to expand this equation now in terms of section 1 and section 2 here, in terms of P2 minus P1 pressure, or in terms of kinetic energy, what I can do is I can expand these terms and divide them throughout by specific weight here. Okay, by specific weight here. And all I'm doing is right now, I'm just spreading out this term, this one, and this one. And let's see what our equation, what our energy equation is going to look like. So we're expanding the pressure term right now, and then we're expanding the kinetic energy term. And this, along with this kinetic energy, we also have alpha here. Alpha here represents the kinetic energy coefficient, and that is used to basically account for all non-uniform velocity profile. Alpha is greater than 1 for all non-uniform velocity profiles, and for uniform velocity profile, the value of alpha is equal to 1. Okay. And I'm expanding the elevation term now in terms of Z1 because I'm looking at the cross-section 1 right now. Okay, so I've written down those terms. Of course, they're going to be added up to each other, and then I take the other terms onto the other side for section 2 of the pipe here, which has a different elevation, and kinetic energy changes would take place, pressure changes would take place, and all we have to do is we just have to equate them both together, and obviously we still will have the head loss term. Okay, so when we're talking about ideal flows where the viscosity of the fluid is negligible, so ideal fluids with negligible viscous effects, that's called the ideal inviscid velocity profile, right? That just means that if we are looking at the velocity profile, it's going to remain constant throughout the radial direction of the pipe. Okay, this is the ideal inviscid flow. For an ideal inviscid flow, we have alpha 1 here equal to alpha 2. Okay, we have alpha 1 equal to alpha 2, which is equal to 1, and this head loss term is 0 for an ideal inviscid flow. And then this equation just becomes the Bernoulli equation that we just saw if you multiply it throughout with specific weight. But we're not looking at an ideal inviscid flow. We have viscous effects that are taking place for our fluid flow here in this pipe. Viscous effects are dominant. So this head loss term here is actually not equal to 0. It's going to stay here. And although the velocity profile And this viscous pipe flow is not uniform. It's not like this. It's actually parabolic, right? We've already discussed that. It's actually parabolic. So the velocity profile is not uniform in the radial direction, but for the fully developed laminar flow, this velocity profile does not change within this pipe. And that is what we're considering right now. So the velocity profile does not change in this direction. Yes, the velocity changes in this direction, but the velocity profile in this direction is not changing. So what we can say is that we can assume that alpha 1 is still equal to alpha 2 for our fully developed laminar flow case. And that means that this equation is going to be equal to this one because the velocity is equal. V1 is equal to V2. The velocity profile is not changing. Alpha 1 is equal to alpha 2. So these two equations become equal to each other. They cancel out. And we are left with, just rearranging this equation, this is the equation that we are left with in terms of the head loss for the flow, okay, the energy loss due to the friction effects. And now I just basically write P1 in terms of, I'm just expanding P1. We already know that P1 is equal to P2 plus delta P, and that's all I've done here. I've just expanded into that. And then this gets canceled out here, okay? And I'm left with this term here, okay? So basically what we're saying is that head loss here is corresponding to the pressure head and the elevation right now, okay? So all I need to do now is I need to write what Z2 minus Z1 is going to be equal to, and I can do that as I've already seen when I've talked about the non-horizontal flow, what that is going to be like. And now, actually, what I can do is that this is why I asked you to remember that equation from earlier, because all I need to do now is this is that equation. I can just substitute the value of this equal to all of this multiplied by this over here, okay? I can just plug that in over here, right? So when I do that, this is what I'm left with. And now I just simplify it further. I write tau in terms of tau w. Go back and look at the previous video for this again. I've just written this, expanded this term in terms of tau w, and now this is going to get canceled out, and I'm going to be left with the head loss terms equal to, in terms of the wall shear stress now, okay? And this is the head loss term, and this is applicable. It is valid for both laminar and turbulent flows because we haven't used any specific assumption that would say that this flow in here is basically laminar or turbulent, other than talking about the alpha terms here. But the alpha terms for turbulent flow are usually equal to 1 as well, so that's why this can also be valid for turbulent flows. And now another thing is, another way to look at this equation here is like this. All I've done here is, okay, this got canceled out, right? But I've multiplied basically this equation here by gamma. Or actually, I haven't even multiplied it. I've just expanded this term because I can write gamma in terms of rho g. That's all I've done here. And this is another way to write head loss, this head loss term here. Instead of writing in terms of tau W, in terms of wall shear stress, I've just written the head loss term in terms of the pressure head and in terms of the elevation within the pipe. Okay. And this is something that is called the change in the height of the hydraulic grade line. Okay. It's important to account for this. It's important to know what hydraulic grade line is, because if you can work with this expression here, it makes your life a lot easier, because you know that the flow is going to go in the direction of the lower hydraulic grade line. Okay, it can be computed at each section within this pipe, like at 1 or at 2. So all you have to do is you have to find out the hydraulic grade line at, say, 1 and the hydraulic grade line at 2, and wherever the hydraulic grade line is going to be lower, that is the direction in which this flow is going to move. So if for this flow in which the fluid is moving upwards, you can say, that means that you should already have an indication that, okay, the hydraulic grade line, the HGL here at 2 is lower than the HGL at 1. And we're just going to look at this in an example so it makes things a bit clearer for you. Let's just look at this example here where we have certain parameters that are available to us, and we are assuming that it's steady laminar flow, and another assumption that we have to make is that this is a fully developed flow, right? If it's not given to us. So we have to first of all verify if the flow truly is upwards or not. I can just make a schematic first just to see and understand what is going on. So let's just assume for now that this pipe is flowing with the fluid upwards right now in this direction, and I have the diameter given to me right now, right, which is 6 centimeters here. I have I don't know the length of the pipe, but it's been given to me that the section 1 and section 2 are 10 meters apart. So basically Z2 minus Z1 is given to me. Okay, I can take section 1 somewhere here, section 2 here. So Z2 minus Z1 is given to me. It's 10 meters apart. It's also given to me that this is at a 40 degrees angle, this pipe. So let me just say that, okay, this is the angle. This is 40 degrees. What else is given to me? I've got pressure at 1 here, because I'm calling this 1. And over here, this section is 2. So I've got pressure at 1 given to me, which is this one. And I've got pressure at 2 given to me, which is this. I've got the fluid characteristics given to me in terms of viscosity and in terms of density. Okay, so yeah, that's what's given to us. And now to verify if the flow is upwards or not, we are going to go with what we just discussed, hydraulic grade line, HGL. So HGL at section 1 is going to be equal to Z1 plus the pressure term divided by the specific gravity. And because I already have the values for this, I can just plug them in. The elevation, Z1, I'm going to assume that it's 0, and Z2 is at 10 meters. So I'm just going to plug them in, and I'm going to find out the HGL at section 1. And I can do the same thing and find out the HGL for section 2. And now what does this show me? Because the HGL at 2 is lower, right? That means that flow goes in that direction, because flow goes in the direction of a lower HGL. And it means that we were right in assuming that the flow was upwards in the first place, okay? The second part is that we need to compute head loss between 1 and 2. And now it's easy enough to do that. We just need to go with this. Head loss equals HGL at 2 minus HGL at 1. And we will get the head loss term here. So just to make a comment on this head loss, the pressure loss is 4.9 meters. And the total length that you're looking at is 10 meters. That means almost half the length of the pipe. And that is a pretty large head loss. And we would usually like to minimize this head loss, okay? So do you understand how, instead of having to use the wall shear stress term, we are just using the HGL, the hydraulic grade line, and it makes our life so much easier. And now I'll just leave part C and part D up to you. You can do that yourself. And I'm going to leave this problem for you as well so you can get some practice in. You have a fluid that is given to you, fluid properties as well. You've given to you that the pipe is inclined, the diameter is given as well, and you have section A and section B at which the pressure, velocity, and the elevation is given to you as well. For example, say this pressure at B, you can assume that it's equal to, let's say, 300 kilopascals, okay? And you have to find out just two things. Which way is this flow going, whether it's upwards or downwards, and what is the head loss through this pipe, okay? So until next time, thank you.